So first of all, I want to check my dimensions to make sure that I'm able to multiply these two matrices. So as a reminder, this is 2 rows by 2 columns. So this matrix is a 2 by 2. This one over here is also 2 rows by 2 columns. So in terms of being able to multiply it, those inner dimensions match. And the outside dimensions tell me how big my answer will be. So when I multiply a 2 by 2 by another 2 by 2, I get a 2 by 2 back. And I'm going to do this the slow way still. This will probably be the last time that I do matrix multiplication slowly. So if you haven't practiced much of it, you know what you can do this weekend, among other things. So I'm looking for a 2 by 2 matrix. And if I label all of those components, this is row 1, column 1, row 1, column 2, row 2, column 1, and row 2, column 2. So to get my answer, that's telling me which row and which column to multiply together. Here, I need to multiply row 1 from the first matrix times column 1 of the second matrix. So I'll have 2 times 1 plus 5 times 3, and I get 17. Here, I'm looking for row 1 of the first matrix times column 2 of the second matrix. Row 1, column 2, 2 times 0 plus 5 times 2. Now I'm under row 2, column 1. Row 2, column 1, I've got a positive 1 plus a negative 3. And last here, row 2, column 2, row 2, column 2, I'm looking at 0 plus negative 2. And I've got another negative 2 there. So that's my answer. That's my matrix. We typically read the numbers in a matrix off by rows. So I would say this matrix is 17, 10, negative 2, negative 2. This is another way that we can write a vector, and sometimes we call it a column vector because we're writing that vector in a column. Let's say that I have a matrix. I don't know, 1, 2, 3, 0, 4, 1, 0, 0, 5. Just trying to make it kind of easy. So if I have this matrix and I multiply it by a vector, 3, 2, negative 1, then looking at the dimensions here, and this is really why we need to write our vectors as column vectors when we're thinking about them with respect to a matrix. So this matrix here is a 3 by 3. And because we wrote this as a column vector, this vector is a 3 by 1, meaning 3 rows, 1 column. That means that my inner dimensions match. So we're okay to do the multiplication. And the outer dimensions are telling me how big my answer will be. Well, my answer is going to be another 3 by 1 vector. So although this is a little bit mathier than we need for 17b, a matrix is a linear transformation that sends a vector to some other vector. So it's kind of like a matrix is performing the role of a function. We can give it a vector, and it's going to spit out a new vector for us. So if I do this matrix multiplication, I know my answer is going to be a 3 by 1. So the thing that goes in my first row, first column is my first row times the first column, where there's only 1 column. So I'm just going to do this really quick. 1 times 3, I get 3. I don't want to keep track of the arithmetic. I get 3. 2 times 2 is 4, and 3 times negative 1 is negative 3. Okay, my second row, I've got 0 times 3, that's a 0. plus 4 times 2 plus 1 times negative 1. And last, I've got 0 times 3 plus 0 times 2 plus 5 times negative 1. And we can clean that up to say through 4, 7, negative 5. So this matrix is acting as a function that takes the vector 3, 2, negative 1 and changes it into the vector 4, 7, negative 5. So there's a question about how I got the negative 1. I'm not sure if we mean this negative 1, I made it up, or if we mean the negative 1 right here. So I'm going to assume it's the negative 1 right here. So this entry is in my second row, first column, because there's only one column here. So I get this by multiplying the second row of my first matrix by the first column of my second matrix. And we pair the pieces up. So I would have 0 times 3 plus 4 times 2 plus 1 times negative 1. So that 8 is my 4 times 2, and the negative 1 is my 1 times negative 1. Well, if I do this matrix multiplication out, I've got a 2 by 2. I wrote a 3. I said the number 2. It's Friday. I'm sorry. I've got a 2 by 2 times a 2 by 1. So I know my answer, these match. My outsides tell me the dimensions. So my answer will be a 2 by 1. And when I do this, I end up with 2 times x1 plus a negative x2, or minus x2. Down here, I've got 4 times x1 plus 3 times x2. Well, that might not be terribly exciting to you. This actually opens up options for us in terms of solving systems of equations. Let's say that I started by giving you a question that I wanted you to solve, and the system of equations that I give you is 2x1 minus x2 is equal to 5, and 4x1 plus 3x2 is equal to 21. Well, this system of equations, by the way, given time, energy, and sufficient monetary motivation, you should be able to, using only your pre-calculus skills, solve for x1 and x2. And if you don't like to think of them as x1 and x2, just write them as x and y. I'm going to give you, I don't know, like 1 minute. One pre-calc option would be, since the first equation, the x2 is kind of almost on its own, we can isolate the x2 and then plug it in down here. So that's one option for getting through this. So I take that x2, I put it over here, so the top equation would become 2x1 minus 5 is equal to x2. Like if I add the x2 to both sides and subtract 5 from both sides, and then we can take that whole thing and plug it in there for x2. So then I'd get 4x1 plus 3 times 2x1 minus 5 is equal to 21. Multiply everything out. So 4x1 plus 6x1 minus 15 is equal to 21. That's 10x1 is equal to, and if I add 15 to both sides, I think I get 36. So x1 is equal to 36 over 10, or like 3.6. And then I could plug that back in to come up with x2. So here's my system of equations. And what we're going to do is we're going to look at that left-hand side, and I'm going to rewrite the left-hand side as a matrix operation. By that, I mean, rather than thinking about this as sort of two separate rows, I'm going to think about this as one grouping here and one grouping here. So I'm going to take this, and that left-hand side, I'm going to write out with matrix multiplication. I'm going to steal the coefficients and say that that left-hand side is equivalent to taking this matrix and multiplying it by the vector x, y. And the resulting vector that we get out is -7, 1. And what we're trying to do is solve for the x and the y. Now comes the fun part. I'm going to show you the way the textbook would do this. It's not actually how I would solve this system, but it's the way the textbook shows it. So, and we kind of need to be able to do this thing for some other stuff. So I'm going to pause and come off to the side to say something really revolutionary. I hope everybody's prepared for it. If 3x is equal to 5, x is equal to 5/3. Unfortunately, we don't have a way to divide by a matrix. We have ways to multiply by a matrix, but not a way to divide. So in our realm where we were just dealing with numbers, if I wanted to isolate the x and get the x alone here, I would divide both sides by 3. But there's a different mathematical operator that gets us to the same place, and that is to take that 3x equals 5 and multiply both sides by the inverse of 3. Well, the inverse of 3 for multiplication is 1/3. So I can get that x by itself, and I'll just squeeze it in here. I can get that x by itself by multiplying both sides of the equation by the inverse of 3. So this is the inverse of 3 times 5. Well, it turns out that when we're talking about matrices, even though we don't have something that is division, what we do have is an inverse. So if I called this matrix A, and I'm going to just call this vector my x vector, and I'm going to call my answer over here the vector b. So b is the vector -7, 1, x is the vector x, y. And if I want to get the x by itself, I'm going to multiply both sides by the inverse of a. So the question you should be asking right now is, what's the inverse of a? The good news is, for those of you that like formulas, in the context of 17b, you're just going to memorize what the inverse of A is for a 2x2 matrix. And this is the version of solving this problem that the textbook gives. It's a little bit messy, which is why I wasn't sure whether Gorski was going to show you this part or not. But it is in the textbook, so we'll just go for it. It also might come up in 17C. It is important that you know how to find the inverse of a 2x2 matrix. So if I have a generic matrix, and I'm just going to call the elements of that matrix A, B, C, D, then there is a formula for A inverse, And that formula looks like 1 divided by AD minus BC times the matrix DA. So we swap that diagonal and we make the off diagonal have opposite signs. There are a couple of important features here. If these are all numbers, then this thing out in front is a number. And we talked about on Wednesday that if I multiply a number by a matrix, we can actually distribute this number into each component. The other key feature here is, just like in 17a, we have to concern ourselves with the domain. If I'm dividing by this number, there's a really special number I can't divide by, 0. So we say that A is only invertible and the other way we say invertible is non-singular if this special number down here is not equal to 0. And because that number determines whether A is invertible or not, we call it the determinant. So AD minus BC is the determinant for a 2 by 2 matrix. As the matrices get larger, the formula for the determinant gets more complicated, but it still serves the same role, that we say that A is invertible if the determinant of A does not equal to 0. And for a 2 by 2 matrix, the determinant of A is equal to AD minus BC. I know there's a lot coming at you in terms of the matrices. We really will be using it in 17C, so we have to cover it, even if Gorski doesn't. So we've got this determinant of AD minus BC. The way I'm going to apply that to this over here, so here's my matrix A, and let's go ahead and find A inverse. First, we want to make sure that that determinant is not equal to 0. So if I look in this matrix, that's A, B, C, D in terms of our formula. So I've got 4 times 2 is 8 minus -3 times 1. We're not 0. We're good to go with the determinant. So this is my matrix A. I need the space. So here's my A, and I'm going to find A inverse by doing 1 divided by 4 times 2 minus -3 times 1 times the matrix. We swap the diagonal, and we make the off diagonal the negative sign. So 3, -1. Putting that all together, so this number out in front, I've got 8 minus -3. That's going to be an 11. So when I put this together into the matrix, I am looking at 2 11ths, 3 11ths, -1 11th, and 4 11ths. So this right here is my A inverse. I'm going to pause for a second in case anybody needed any of this in your notes. Take a quick screenshot if you need it. So I need the space to actually solve this system of equations. Going once. Going twice. Okay, I'm getting rid of it. So finally, I'm ready to solve this system of equations by taking both sides and multiplying it by A inverse. When I do A inverse times A on the left-hand side, the matrix and the inverse cancel each other out. Just like if I have 3 times 1, they cancel each other, sorry, 3 times 1/3, they cancel each other out and I'm left with a 1. When I have A times A inverse, they cancel each other out and I'm left with the identity matrix. We'll talk about that in a second. It's the 1 of a matrix. So here, I'm going to be left with X, Y. The thing I'm trying to find is equal to that A inverse matrix. So 2, 11, 3 11ths, negative 1 11ths, 4 11ths, times negative 7, 1. I'm looking at a 2 by 2 times a 2 by 1. Those inner dimensions match. The outsides tell me my answer is a 2 by 1. So I get 2 11ths times negative 7. So that's negative 14 11ths plus 3 11ths. On the bottom, I've got negative 1 11th times negative 7. So that's positive 7 11ths plus 4 11ths. And if we clean that up, negative 14 11ths plus 3 11ths gives me negative 11 11ths. 7 11ths plus 4 11ths gives me positive 11 11ths. And my answer is X equals negative 1, Y equals 1. Imagine that out there in the wild in Australia, we've got this wild population of koalas. And over here, I'm just going to call them the babies. We've got baby koalas. And then we've also got juvenile koalas and adult koalas. And someone is out there studying their population dynamics, and they've taken a survey, a point in time, and they know how many babies, how many juveniles, and how many adults are in that koala population. But they've also looked at the dynamics of how things are changing, and they want to be able to predict how many in each age category there will be 10 years into the future if those dynamics keep up. So we're going to make up the population dynamics. I say this a lot. I do not have a background in zoology. I know nothing about koala populations in the wild. So we're just making this stuff up. I'm imagining that of all those baby koalas, maybe something like 50% of them survive to be juveniles. So we've got these baby koalas, and 50% of them are going to survive to be juvenile koalas. Now the juveniles, they've been around for a little while. They're faster, they're bigger, they're better at finding the right kind of eucalyptus leaves to eat. So maybe that juvenile population, actually like 80% of them survive to be adults. I don't know how long koalas live, but I'm going to assume that like it's not like they only live to be 2 years old, right? So some of those adults are living for a long time. So let's say that maybe 90% of those adult koalas live till the next year. So we kind of took care of the babies become juveniles, the juveniles become adults, some of the adults stay adults. But the missing piece here is we also have to make more baby koalas. So from this juvenile population, I don't know when koalas reach reproductive maturity. Let's assume that juveniles do not have reproductive maturity, so juveniles cannot make new baby koalas. However, our adults can. And let's say that on average, each adult has, is it like a litter of koalas? I really do not have the terminology here. But let's say, for the sake of argument, that these adults produce on average 2 koalas? Well, this is what we call a dynamic system. And we can represent this dynamic system with a matrix that's getting multiplied by a vector. So we're going to do this the slow way, and then we'll write it as a matrix. So the first thing I'm going to do is just write out what the system of equations would look like. And I'm going to rely on something from 17a, which is the idea of a recurrence relation. So if I want to know how many babies I have next year, I'm going to be looking at how many babies I have this year, how many juveniles I have this year, and how many adults I have this year. So to get the number of babies I have next year, well, babies can't produce babies, so that would be 0 times the babies I have this year. We said that our juveniles can't produce babies, so that's a 0 times my juveniles producing babies. But my adults, on average, for each adult, they're producing 2 babies. So 2 times the adults I have right now is going to give me how many babies I have next year. If we do this for our juvenile population, well, how do we get juveniles? Babies grow up. So 50% of our babies grow up to be juveniles. So I'm looking at 50% of our babies grow up to be juveniles. As much as they would like to, our juveniles do not get to remain juveniles, they grow up. And our adults don't get to go backward in time. They are stuck as adults, so none of the adults go back in time to become juveniles. Now to figure out how many adults I have next year, babies don't get to magically just grow up and become adults. They got to spend some time being juveniles, get their wits about them, and then become adults. So my adult population doesn't come from my babies, but 80% of my juveniles grow up to become adults. And of my adult population, 90% of them survive another year. Well, we can take this system of equations or this dynamic vector diagram, and either one of those turn into a matrix. And my matrix is going to look like, we're going to steal all of the coefficients. So I'll have 0, 0, 2, 0.5, 0, 0, 0, 0.8, 0.9 times the vector that represents my population distribution. My babies right now, juveniles right now, and adults right now. And doing the matrix multiplication, the answer that we get out of this is going to tell us, I really didn't leave myself a lot of room here, how many babies I have next year, or time plus 1, how many juveniles I have next year, and how many adults I have next year. Then what it means to be an eigenvalue and eigenvector, and they come in pairs, is that there's a special relationship where multiplying A by a very specific vector is equivalent to multiplying that vector by a number. So there's a formula for finding this, and we'll talk about it more on Monday, but if I need to find lambda, which is the eigenvalue, oops, I can't spell today, which is the eigenvalue, we find that by setting the determinant of A minus lambda I equal to 0. Now this right here means we take our matrix A, 3, 3, 2, 8, and we subtract off the matrix lambda, 0, 0, lambda. We're always subtracting this same matrix. We'll do the subtraction of the matrices first, and then find the determinant using our formula. So when I subtract those matrices, I get 3 minus lambda, 3 minus 0, 2 minus 0, and 8 minus lambda. Now, taking the determinant, we do A times D minus B times C, minus. So I've got 3 minus lambda times 8 minus lambda minus 3 times 3. You set that equal to 0. For a 2 by 2 matrix, this is always a quadratic equation. Best case scenario with factors, worst case scenario, you end up using quadratic formula. This is how you find that thing called an eigenvalue.